Hello and welcome. The other day I've done the integral of 0 to 1 x to the x dx, and it turned out to be this infinite series. The only difference was it had alternating signs. So I thought to myself afterwards, what happens if I put the x to the x at the bottom? And I got this one, but the workings are practically identical. I mean, the DNA of the question is 90%. So I'm sorry I'm being repetitive. Practice makes perfect, and saying the same thing again might reinforce the thing. So since I wrote the question now and I put it into one of my books, I'm gonna just present it. So I'm awfully sorry. It's if you've done the integral 0 to 1 of x to the x, then it's practically the same. Okay, so the way we start with this question, and I'll take you back to the that particular question, is to actually write this as, first of all, x to the minus x dx, and then bring exponentials in. So 0 to 1, e to the log x to the minus x dx, and then bring a minus x log x totally on the exponent. Next thing, as in the question before, is to actually write this as a power series. So if you think about the power series of the exponential with a minus, now what will be happening in there is we're going to have, first of all, a alternating so let me just write so we can all see this. So e to the minus x is, of course, 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4 over 4 factorial. Perhaps I shouldn't have used x, so I've used a different letter. So your x is all of this, basically. So if I write in compact notation into sigma, that is from r is equal to 0 to infinity, we're going to have the alternating term. I want to sort this out whether it's r plus 1 in a minute. And then we're having, of course, the rest of the bit in there, and that is going to be, of course, an x log x to the power of r divided by r factorial. So that's the 0 factorial, which will give me, of course, if r is equal to 0, it's going to go positive. So it's correct. We can leave it like that. And then, of course, we have the dx. So that's that is the same as that, written as a power series from your further maths. So now we're going to interchange summation and integration. So first of all, the sigma written first. So in here, what do we have? We can pull outside the integral anything that doesn't have a x dependence. So we can pull the minus 1 to the r over r factorial, and then the integral 0 to 1 x log x to the power of r dx. Okay. And this is the bit now we've done a million times. I think it's the third time I'm doing it in the last week, so I'm getting a bit fed up with that. We're going to use a substitution, and the substitution for this to change to a gamma function, in particular the limits, is to use the substitution. Let's say t equal to the minus log x, or minus t is log of x, or x is e to the minus t. So as part of your substitution. And then the dx is minus e to the minus t dt. And the limits 0 and 1 will map. 0, which one can we use? We can use this one. Pardon me. When putting 0 in there, log of 0 is minus infinity, with a minus will go plus infinity. That's the whole point why we put a minus in there. And 1, log of 1 is 0, minus makes no difference. So far we got that. So if we need more stuff, we'll come and get it. So we got, this is just merely being copied. r factorial, and then the integral. Now we're gonna, oops, I'm rushing a little bit there. The 0 goes to infinity, this goes to 0. X is e to the minus t from here. Log of x is minus t, and all of this needs to go to the power of r, and the dx is another minus e to the minus t dt. Okay, equal sigma r is equal to 0 to infinity. And now we're gonna have this minus, not this one obviously because that's power to the r. I can use to swap the limits, 0 to infinity, the right way around. Then I'm gonna have e to the minus rt, that's this exponential. And then this minus, I'm gonna do it on the next line. So I'm gonna have, obviously the minus from there has gone, so I'll go e to the minus t, and then I have a minus t to the power of r dt. And I'm moving now from this line here, sigma r is equal to 0 to infinity, minus 1 to the r. Now, this minus 1 to the r, I can put it also to the r outside the integral. It has no, sorry, it has no t dependence. And r factorial. And this now lives inside the integral e to the minus t r plus 1, and I've got, of course, the t to the power of r dt. Now, this is some kind of gamma. It just needs a little bit of adjusting, so we have the right quantities in there. So let's rewrite, first of all, that bit in there. That, of course, we can throw away. I hope you can see it before I write it, but I'll write it. So for completeness, that's minus 1 to the power of 2r over r factorial. And of course, that's minus 1 to some even power, so that's 1 on the next line. And then we're going to use another substitution. And because we have no space, this will not be visible if I carry on writing further down. So what I'm going to do, I'm going to write it up here. And the substitution is, remember, the gamma of x is defined as 0 to infinity e to the minus, let's say u, and then u to the x minus 1 du. So if you look at what we've got in there, we've got almost this, but we wish we had a single letter there, a minus t, a minus u, or something like that. So we are going to call all of this lump, since we've got u there, I might as well use u again. So we're going to say, let u equal to t r plus 1. Our du, this is now just simply r plus 1 dt. So we want to add dt is equal to du over r plus 1. Remember, r plus 1 is just not a constant, but it's not a variable in the sense that it affects this integral. Pardon me. 0 and infinity, the limits. 0 if, what are these? These are in t. So when t is equal to 0 here, u will also be 0. And when we have t becoming positively infinite, so does u. So the limits do not change really. So let's put them again, 0 to infinity, unchanged. E to the minus u, all of this is u. And the t, now the t needs to be changed as well. I haven't done it up there. So t is u over r plus 1. So that is that bit in there. So all of this now will be u to the r plus 1, all to the power of r, and the dt is du over r plus 1. And now, more tidy, sigma r is equal to 0 to infinity. This, or we already said, is 1 because it's an even power, so I'm not going to write it. So it's 1 over r factorial. Now, other bits now that do not have dependence on u, which are just these r bits that we got in there. So we got 1 over r plus 1 to the power of r plus 1. Let me just write what I got left and then we'll check it. 0 to infinity e to the minus u and then we got u to the r du. All I've done in there, we got this 1 over r plus 1 to the r, but we have another 1 over r plus 1, so that's the plus 1 on the exponent. So it will make r plus 1 at the bottom to the r plus 1. And once we pull that outside, of course, we'll have just left there the u to the r and the bit that we got in there. And I don't think, it might not be visible on the video, so I cannot see it at the moment. So probably I will clear the lines above, and hopefully we'll finish this off. I apologize, this is shaking. So let's check if we're still in the middle of the board. Yeah, it's not too bad. Okay, so that's 0 to infinity. I rubbed it off as I touched it. Okay, so this is now equal to, now this is a gamma function. The gamma of x, I shouldn't really have rubbed it off. The gamma of x is, of course, the integral from 0 to infinity. And if I write it in u, it will be e to the minus u to the x minus 1. So basically here I have the gamma of, let me just write all the bits, the gamma of r plus 1 really. So we go sigma, r is equal to 0 to infinity. We got loads of rubbish really. R factorial 1 over r plus 1 to the power of r plus 1. And then this is the gamma of r plus 1 by definition. And of course, if this is an integer value, the gamma of n plus 1 is the same as n factorial, or part of the gamma function work. And therefore, this is equal to sigma from r is equal to 0 to infinity, 1 over r factorial. And you can see what's going to happen. R plus 1 to the power of r plus 1. And that, of course, is your r factorial. Goodbye, my friend. And all we're left with is, of course, this is equal to the series that we got above. So if we go from r is equal to 0, 1 over r plus 1 to the power of r plus 1, which perhaps it'd be better if we start the summation from r is equal to 1 to infinity and write it as 1 over r to the r. That's double checking that it does give us the right quantity. If r is equal to 1, we're going to get 1. If r is equal to 2, it's going to give us 1 over 2, and so forth. So it's probably better to write it like this. We're just shifting the origin basically. I hope you followed this one. I think I do apologize. Is very, very similar to one I've done recently, but it's practice makes perfect, and it's good to see it again. So I'm going to be signing out, and I'll see you real soon with more videos in maths. Bye for now.